Hi guys, I am Dr. Nandabalaji. Today we are discuss about the topic of crystal structures. In this topic, as like as single crystals. First of all, we know that the crystal structures. Last video we have know the crystal structures and lattice points and basis points. Like as the figure as shown in the lattice point and lattice point and basis point as combinations of crystal structures, and we discuss about this topic in this video like as the introduction of crystals, single crystals and unit cell and seven crystal systems, and why we need to categorize the crystalline materials like as single crystals and polycrystals, and importance of crystal systems. First of all, importance of crystals, single crystals. First, we are understand the fundamental properties of crystal structures and the types essential for advancing materials. Each crystal type plays a vital role in various applications, driving innovations and technologies. In the crystal structures images as shown in the figure, in the single crystals in the figure 1, its arrangement of atoms or molecules or particles, it's evenly like as row and columns are evenly fixed. But polycrystallines are evenly fixed, but the grain boundaries are changes. So this is the some difference like as atoms repeat almost perfectly for the entire materials. It's like a single crystals. In polycrystals, atoms repeat with the grain. Grains are separated by grain boundaries where the repetitions, and the explorations of single crystals, regular and periodic arrangement of points in three dimension. Crystals have a three-dimension nanostructure material. So the single crystals are regular and periodic arrangements of points in three-dimension structure, identical surrounding to that of every other point in the array. In the figure shows the graphical approaches of lattice point. The atoms or molecules are evenly distributed. The length and the cross-sectional length of each and every point has been the same. So this is shown in the figure, and the fundamentals of building blocks like as repeating its own dimensions in various directions gives crystal structures. In this, atomic structures are shown in the figure. In this figure shows in the body center cubic structures and face center cubic structure and single cubic structures. The cubic structures, the atoms are arrayed in the circular path of the fruit, like as the shown in images. And unit cell. What is unit cell? Like as lattice parameters. X, Y, Z. Crystals are three-dimension material. So the crystallographic axis has X, Y, Z directions. Length of the unit cell along the X, Y, Z direction are A, B, and C. And integral axis alpha, the angle between A and B, beta, the angle between B and C, and gamma, the angle between C and A. In these parameters like as A, B, C, length of the unit cell, and alpha, beta, gamma angle in internal axis axial angles are collectively known as the lattice parameters. In this lattice parameter, a unit cell consists of only one full atom. A primitive cell got the points or atoms only at the corners. If a unit cell consists more than one atom, then it is not a primitive cell. Example of primitive cell like as simple cubic structures. Example for non-primitive cell like as BCC, body cubic centers, and face center cubic unit cells. In this diagram shown in the primitive cell of simple cubic structures and non-primitive cells of body center cubic sector, side center cubic structure, and face center cubic structure. Let's explore the unit cells are classified into several categories based on their shape and dimension. The primary type include simple cubic, body center cubic, face center cubic, and hexagonal closed package system. Each type exhibits unique properties and arrangements of atom, influencing the material stability and interactions. Like examples of phase center cubic structure elements at room temperature like as aluminum, nickel, copper, these type of metals. Examples of body center cubic structure element at room temperature, uh, lithium, these type of materials. An example of HCP element at room temperature like magnesium, zinc, zirconium, gold, these type of materials. And what is seven crystal systems? Crystal system categorize crystals based on their symmetry and geometry properties. The seven major systems are cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, and triclinic. Each system presents unique symmetry elements that influence the arrangement and bonding of atoms within the crystal. In these seven crystal systems are separated into two different parameters like as A, B, C length and alpha, beta, gamma angles. In cubic structure, A, B, C length are equal, alpha, beta, gamma are equal to the 90 degree, and tetragonal structure like as A, B and C. The length of AB is equal, C is not equal, and alpha, beta, gamma is equal to 90 degree. And monoclinic length of ABC it's not equal, alpha, beta, gamma. The alpha and gamma is 90 degree, but beta is not equal to 90 degree. And orthorhombic structure ABC length it's not equal to length alpha beta gamma it's equal to 90 degree. In triclinic length of ABC are equal, alpha beta gamma it's not equal to 90 degree. In hexagonal AB length is equal but C is not equal to another length, alpha beta it's equal to 90 degree but gamma is 120 degree. In trigonal structure, A, B, C, it's equal, lengthwise it's equal, but alpha, beta, gamma, it's not equal to 90 degree. Importance of crystal systems. Classifications of crystals. Crystal systems help classify and organize all crystals into seven groups based on symmetry and lattice parameters. Understanding physical properties, many physical properties like conductivity, refractive index, and elasticity depend on the crystal system. Prediction of material behavior, knowledge of crystal systems aids in predicting how a material will respond to external force, like as mechanical, thermal, or electrical predictions. Applications in technology, crystal systems are essential in designing semiconductors, lasers, and superconductors, where symmetry plays a very vital role. Foundation for crystallography, they form the basis for studying atomic arrangements, X-ray diffractions, and material characterization in science and engineering methods. In the summarization of crystals, classification of solids crystals in the single crystals like as seven crystal types: cubic, tetragonal, orthorhombic, hexagonal, robohedral. Importance of crystal systems like as classification of crystals and